Welcome to qnawire.
Okay, we have two compounds, 5 and 6. The first, number 5, frequently referred to as diphenylmethylene, right? CH2s are methylene, and so it's like a methylene with a phenyl on each side. That's diphenylmethylene. And the pKa for one of the protons on diphenylmethylene is about 32. Okay, we also have compound 6, known colloquially as phenylacetone. And recall that in any alpha carbon of a ketone, especially one that is next to a electron withdrawing group, such as a phenyl ring, the pKa is going to be around about 20, but in this case, probably lower. In either case, it's going to be far lower than the pKa of our diphenylmethylene. So let's just say 20. That's a very good estimate. So what that tells you is that these protons are more acidic than these protons. And so the question then becomes, let's compare the relative stability of the corresponding conjugate bases. So deprotonation of diphenylmethylene, deprotonation of phenylacetone. Let's look at the conjugate base. Right, we get a lone pair here and a negative charge. And essentially, this negative charge can travel to many locations within this ring. I will show one. Right? And so we can shift the negative charge here, and we can continue to do so, eventually shifting the negative charge all around the ring, which in fact, I think the easiest way to visualize this is to think about it in terms of a delocalized negative charge, in which we can end up with a partial negative here, partial negative here, partial negative here, a partial negative here, a partial negative here, a partial negative here, and a partial negative here. Those are all the locations that can end up formally with a negative charge. Okay, now let us consider the conjugate base of our phenylacetone. So following deprotonation of the alpha carbon, negative charge here, lone pair. Okay, and this lone pair or negative charge can, like in the case of diphenylmethylene, find resonance throughout the ring. Okay, but that's not very exciting. We already know what that looks like. And we know that because this pKa is very low and it only has one ring, that the ring side must not be the important part, right? Because if it only has one ring, as opposed to the two of diphenylmethylene, we wouldn't expect the pKa to be so low. So what is lowering this pKa so drastically? It is the carbonyl functional. And that is that this can turn into an enolate, in which the lone pair becomes a double bond between the alpha carbon and carbonyl carbon, and the double bond between carbon and oxygen swings up onto the oxygen to generate this important resonance structure. The enolate, in which we have placed the negative charge formally on oxygen. Recall that oxygen is very electronegative, and that's what provides the increased stability of the negative charge in phenylacetone as opposed to diphenylmethylene, and therefore increases the acidity phenylacetone as compared to diphenylmethylene. There we go. So the most relevant and most stable resonance structure is that.